I will talk today about briefly on the mining side of rare earth mining, and then I will focus on physical concentration processes and chemical separation processes. As Caleb said, I'm an associate professor from Missouri University of Science and Technology. I joined the University of Missouri in 2012. Before that, I was at the University of Alberta in Canada working on the oil sand processing. And my focus since I joined Missouri S&T was mineral processing. My background is in chemistry. And so I love to use my chemistry knowledge actually to improve the processes, water-based chemical separation processes that they focus mainly on surface chemistry. And also I do some materials engineering work in my lab, like in making novel chemicals to aid the separation processes. So my lecture today will I will start with an introduction, brief introduction, and then I will talk briefly on rare earth mining, and then physical separation processes, and then chemical separation processes, which is mainly the hydrometallurgy part and solution purification in brief, and then I will end up with conclusions and questions. So as we all know, it is almost impossible to avoid a piece of modern technology that does not contain rare earth elements. And as shown in this slide, the periodic table highlighting rare earth elements that are further categorized into light rare earth, medium rare earth, and heavy rare earth. So this classification is based on the atomic mass of these elements. Usually, there are other classification methods for rare earths. Usually depends on their, as I said, one of the classification depends on their variation in atomic mass, and other classification based on their other chemical and physical properties, like, for example, electron configuration, solubility, and other stuff. You can see here the light rare earth, the medium rare earth here, light rare earth, it's called Zurich group, and then the heavy rare earth here that have the larger atomic masses, and then in the middle, europium, samarium, and gadolinium. Additionally, in this figure, we can see the abundance of different elements. And when we add the relative abundance of rare earth elements, usually it is addressed against as a function of as a function atoms of rare earth per millions of silicon atoms. So silicon is the most abundant element after oxygen. So that's why the abundance is addressed in terms of or per the availability or abundance of silicon atoms. So if you see, this analysis shows that these rare earths are not that rare. And as noted, some of them, they are more even abundant compared to gold and have similar abundance compared to copper and lead. But the problem of them of rare earth processing and production is the complex mineralogy, the low concentration first, and the complex mineralogy of their ores and their minerals. So that's why they are called rare earth elements. So rare earth elements are critical elements, and when it comes to critical material, usually each country, they have their own critical material list, and the criticality of the material is usually evaluated in terms of supply risk, environmental implications, strategic application, and other factors related to security concerns in terms of economic prosperity and possible political tension. Usually, among all the critical mineral list, rare earths elements are always there. And one of the most famous now, because I attended so many presentations about critical elements and stuff, and almost all the presentations share this nice graph that was developed by Nassar in 2016. And this actually showing the criticality index for several elements, where they show the supply risk of these metals as color-coded, from blue, which is low criticality, and red, which is high criticality. So as you see here in the x-axis, the disruption potential, and in the y-axis, the economic vulnerability of these elements. And again, the supply risk is showing that the supply risk is dependent on the trade exposure, which is the market value, and disruption potential, and economic vulnerability, which is instability of the market. The point size here represent trade exposure, and the point color represent, as I said, supply risk. As you can see here, some of rare earth elements like neodymium, praseodymium, and dysprosium, in addition to yttrium and lanthanum, they are really have high risk of disruption potential and trade exposure and supply risk compared to other rare earth elements. Okay, so this was the introduction. Now the mining, I will cover give an idea about some deposits and minerals. And I meant to actually give example of these deposits. So I will, because I will discuss some flow sheets associated with processing of some of these deposits and rare earth ores. First of all, this is, I saw this in the previous presentation. So this is a nice actually figure showing the main RE rare earth production in blue circles and the separation facilities in green circles. And we all know that China produces more than 60% of a global supply of rare earth. US produces rare earth concentrate, but it is now shipped overseas for processing and production. Mountain pass material will soon have large refining capacity to produce rare earth from their mountain pass concentrate. And this graph showing again the rare earth reserve. So you can see here the global rare earth reserve. So you can see that China, it has more than 1/3 of the global rare earth reserve. And for the production, it's even worse because it showed that about 80% of rare earth is produced from China, in China. Some of rare earth minerals that are, so rare earth are contained in so many types of minerals, but the most common minerals are bastnasite, monazite, and xenotime. And this table, maybe for the people that are looking at the screen from the room, it's not that clear, but there are several types that contain rare earth minerals. Some of them, they contain light lighter rare earth, some of them heavier rare earth. So for the rare earth deposits, I will discuss 3 famous deposits. One of them is located in USA, which is the Mountain Pass, USA, which contain usually 8 to 12% of rare earth oxides, and the relative abundance of different rare earth oxide within this deposit is shown here. So if, lanthanum, for example, 33%, 0.8% of rare earth oxide is lanthanum oxide, and about 50% is cerium. So bastnäsite here is more or contain more lighter rare earth element than heavier rare earth elements. The other deposit that is also one of the largest, or the largest actually, deposit for rare earth metals, which is responsible for about 45% of global rare earth metal production, is the Bayan mining district in China. And you can see the relative concentration of different rare earth oxides in this table. So usually in this type of deposit, we have the monazite, which occurs as a minor mineral in granite, igneous rocks, and other metamorphic, and also in other metamorphic rocks. The third one is the Mount Weld in Australia. Usually the rare earth elements include monazite, apatite, which is type of phosphate minerals, that also consider a good host for monazite minerals, synchesite and schistite. So in this type of deposit, the light rare earth elements are usually found associated with monazite, while the heavy rare earth elements are mostly found in schistite. Other sources of rare earth metals or elements is the ion adsorption clays. In this case, these are formed by weathering of granite and other rocks, and the REE usually absorb on the surface of these clays, mainly kaolinite and illite. And you can see the relative concentration of different rare earth oxide in this, like the average concentration, or in these type of sources. And it is mainly found in China. As for processing, now I will talk about processing. I will, in general, the processing of rare earth start with mining, which is extraction here in this flow sheet. So this include blasting and drilling to extract the rocks or the ores that they have acceptable concentration of rare earth that can be processed. Then the ore undergoes comminution. So comminution is a term that is usually used to describe the size reduction and liberation of minerals. So in this case, it's done by a comminution process, is done by crushing, more than one stage of crushing, and then followed by grinding. We may need in some flow sheet of regrinding after physical separation to further liberate the minerals. So after grinding, the beneficiation of the liberated ore occur via different stages of physical separation processes. So beneficiation is a term that is used to describe the physical separation, not the chemical separation. So you are actually concentrating the mineral. You are not, you don't have any chemical transformation of that mineral that contain your valuable metal. Usually different techniques are used for beneficiation of rare earth. And all of these techniques employ the difference in the physical properties between the rare earth minerals and other minerals that are found in the ore. And this include gravity separation, so where the separation depends on the difference in density between the various mineral, or magnetic separation. Again, that the separation principle focus on the difference in magnetic susceptibility. And we know that a lot of rare earth minerals are paramagnetic, so they can be concentrated using a high intensity magnetic field. Electrostatic separation, which utilize the difference in polarity or conductivity between the minerals. And then flotation, so which is the most selective, famous type of physical separation process that is used extensively in separation of physical separation of rare earth. And it is a physical separation method, not a chemical separation method, although that we are adding so many chemicals in the flotation to enhance the selectivity of the process. Then the concentration after beneficiation goes to leaching, using either depends on the mineralogy of the ore, leaching, and either using inorganic acids or alkali solutions or so. And then after that, of course, solid liquid separation followed by solution purification, where you can separate the rare earth salts from other salts that are in the leachate solution. And this is done by different techniques, include ion exchange. I will discuss crystallization, and then the solvent extraction. I'll focus more on solvent extraction. After that, you can separate to get rare earth compounds, pure rare earth compounds, and then at the end, you have to process them in a way for metal, to produce rare earth metals at the end. Now, pyro and biotechniques, high temperature pyro and biotechniques are used sometimes, but they are not commercially available. So again, for mineral processing, as I said, the processing of rare earths involve mineral processing, which is a physical beneficiation, hydrometallurgy, sometimes low temperature pyrometallurgy, which mainly roasting or calcination, to convert the rare earths. For example, in the case of roasting, in general, roasting is a process when you convert sulfides to oxides in excess of oxygen, while calcination is converting sulfates or carbonates to oxides, but in absence of oxygen. So sometimes roasting is done before leaching, or to enhance the leachability or solubility of the material. And sometimes calcination is done for feed preparation if you want to remove some, in general, in mineral processing or hydrometallurgy, to remove carbon-based material. Again, gravity separation is actually suitable for beneficiation technique in the case of rare earth physical separation, due to the relatively large specific gravity of rare earth minerals or rare earth pairing minerals compared to other associated gang minerals such as silicates, for example. One of the most famous flow sheets that gravity separation is used is when you process the beach sand. So you apply gravity separation to remove heavy material, and they are used spiral concentrators to produce a heavy part of the or heavy concentrate that contain heavy minerals. As I said, electrostatic and magnetic and flotation also are used to upgrade the concentrate. And I have here a flow sheet. I'm not sure if you can see it clearly. I can't enlarge it more because of the slide. But this basically showing the physical beneficiation of monazite or rare earth or containing monazite, or beach sand containing actually monazite, by a combination of gravity, magnetic, and electrostatic techniques. Usually, a gravity separation is applied to remove the heavy part, and the gravity equipment here, for example, these are some options for different processing options. But if you look at this, shaking table is a type of gravity separation equipment that can also be used to separate minerals based on the difference in density. So usually gravity separation followed by magnetic separation. So depends on what you have in your material. Sometimes low intensity magnetic separation is used if you have magnetite, for example. Magnetite is a ferromagnetic material that can be concentrated using a low intensity magnetic separator. If you have hematite, you need to use high intensity magnetic separator, or other maybe magnetic material such as ilmenite or so you can use high intensity. They are paramagnetic material. Electrostatic separation also is used as part of this flow sheet to separate conductive versus non-conductive material, to separate conductive and non-conductive material, and to end up with monazite, for example, at the end here. Monazite is conductive material while zircon is non-conductive. So it is removed. We'll end up here by concentrating monazite. Now, the details of the flow sheet for beach sand is different from allocation to allocation. And again, depends on what is the mineralogy of your, or what are the different minerals that exist in your field. Froth flotation process is key to beneficiation in rare earth. So froth flotation, again, it's a three-phase separation process. It is more complex. So the design of flotation circuit or flotation plant is more complicated compared to other physical beneficiation like gravity or magnetic separation or other physical separation processes, but it is highly selective. Ideally, I mean, in the lab, you can float anything from anything. By understanding the nature of your material and by modifying the surface chemistry of the different components of your material, you can float anything from anything. But the challenge is how to upscale the process. So for the people that are not familiar with the Froth flotation process, it is an ore that is you bring your ore and mix it with water at a specific solid concentration, and then you add different types of reagents. So the idea of adding all of these reagents is to modify the surface properties of different minerals at these three interfaces. So some mineral will be hydrophobic and will attach to air bubble and float, while the other minerals will stay in the pulp, will be hydrophilic or can be removed in the tailing. So it is not as simple as this, because you have to understand the surface chemistry of these different materials that you have. And you can see here, actually, this is the air bubble, and this is the hydrophobic material that is attached to air bubble. And this shows the relative size, actually, of the material of the your mineral particle and the size of the bubble. In conventional flotation cell, the size of the bubble is between 0.5 to 2 millimeter in diameter, which is about 2,000 micron or so. And then the optimum size for the mineral in flotation operation depends on the ore itself or the mineral that you want to float. Usually, for example, if you want to float sulfide minerals, the size is between 90 to 75 micron. If you want to float phosphates, is between 125 to 90 micron. It depends on the nature of the material that you want to float. But again, you have to add first, before when you mix your ore with water, you have to modify the pH, because when you add the collector is added to render the surface of the mineral hydrophobic. In order for the mineral to be attached to air bubbles, it has to be hydrophobic, because the interaction between the mineral surface and air bubbles is through hydrophobic interactions. And then the frother is at the end. You can add to stabilize the froth, because usually your froth is formed here, and then it will rise. It has to have a specific stability to resist the rupture between of bonding between the mineral particles and the air bubbles. So it has to have some sort of stability to be able to rise to the top and then be collected. Stability, of course, and mobility. But too much stability is bad, because you will have more challenges in the next or the consequent separation, especially when it comes to solid liquid separation, when you have the concentrate and you have to separate solid from liquid. So there is an optimum value for in any process for froth stability. Again, this is picture showing the froth flotation process. This is the froth. You can call it concentrate. And the concentrate is actually, this froth consists of solids, consists of water, and you can still see the air bubbles. And by the way, the shape of the froth can tell you about how good is your selectivity of the flotation process. Because if you have for example, ultrafine material, it may entrain into the froth layer, not as a result of a true flotation, but as a result of a mechanical entrainment because of the small size. So usually, if the froth has hexagonal shape, then it is of a good quality. If it is more like a foam, then it means that it is maybe less. It has a poor quality. Here is some of the collectors. Again, the collectors are added to render the surface of the mineral hydrophobic and enhance the attachment of the mineral particle with the air bubble, and of course, improve the flotation efficiency. And in some cases, you have to think about kinetics also in this. When you design your flotation operation, you have to think about kinetics as well. A shorter time, it means that you are going to have maybe higher recovery but poor grade. Longer time, it means that you're going to have maybe more, again, shorter time, more retention time. Actually, it's gonna negatively impact your the concentrated grade. So you have different in this table, you will have different types of collector that are usually applied in the flotation of rare earth. And this is the working pH range for them. Again, the working pH range is very important to think about when you design your flotation for any mineral concentration process, because there are specific pH value outside this range. Outside that range, there will be limited interaction between the collector and mineral surface. So you have to think about this when designing your flotation circuit for any mineral. Here is a flow sheet showing the best inside beneficiation, actually, at Mountain Pass in California. So usually the Mountain Pass is currently mined using conventional open pit method. So the concentrator flow sheet include crushing, grinding, and then 6 stages of conditioning, as you can see here. They have 6 stages of conditioning. So, and during the conditioning stage, you add your collectors, you add your dispersant or depressants. Depressants are added to inhibit the flotation of the mineral that you don't want to float, like, for example, silicate minerals and other material that you don't want your concentrate to be contaminated with. And then this is done under steam because to improve kinetics and improve the interaction between the collector and the mineral surface. So after these 6 stages of conditioning, then the feed goes to rougher flotation. And you can see here the pH is about 8.8. and the solid concentration is 30 to 35%. After rougher concentration, so the first stage of concentration, the concentrate that has rare earth mineral go to cleaner flotation to further clean your concentrate. So usually in 2021, the concentrate that total rare earth concentrate produced by this process has a recovery average 69.8, averaging 61.2 of total rare earth oxides. And at the end here, 60% of rare earth oxide goes for further processing actually, and it is usually leached using HCl at pH 1 to dissolve the carbonate minerals. And then the product go for thickener for solid liquid separation, and then filtration and drying, and then at the end you'll have about a concentrate that averaging 70% of total rare earth oxides. That goes for shipped for production. Another flow sheet of beneficiation at Bayan Abu deposit or in China. It is actually the type of ore here is more difficult to process compared to the mountain pass one. And as you see, there is a little bit more details or more steps for the separation. Physical beneficiation include the use of low intensity magnetic separator and high intensity magnetic separator. So after crushing, grinding, and then size classification, so the feed goes to the limbs, we call it limbs, rougher to remove magnetite, and then the concentrate is cleaned by the second stage of magnetic separator, and then followed by high intensity to remove hematite, and then another cleaning stage for the hems cleaner, and then after that the feed goes to the flotation, which also involve rougher scavenger. So scavenger circuit is usually utilized to improve that or to increase the recovery or maximum the recovery, while the cleaning is to improve the grade or the quality of the concentrate. At the end, they will collect a rare earth concentrate that has rare earth oxide about 60%, averaging 60% of rare earth oxide. Hydrometallurgy of rare earth, which is a chemical dissolution. We discuss physical separation to produce a concentrate of that has mainly rare earth oxide. Now the hydrometallurgy part of the processing involve leaching and solution purification in order eventually to have a pure rare earth compounds. So leaching actually, or the agent for leaching involve alkalis like sodium oxide or sodium carbonate, or the use of inorganic acid like hydrochloric acid, sulfuric acid, and nitric acid, while the purification involve mainly, these are the commonly used method for solution purification in the case of rare earth processing: ion exchange, crystallization, and precipitation and solvent extraction. If you are not that much familiar with ion exchange is usually resin. We call it ion exchange resin. It is like a sponge that has two parts. One of them is fixed, and one of them is mobile. So the mobile part has ion that can be exchanged with other ion from solution. So when you exchange these ions from solution to the ion exchange resin, it means that you are removing the ion you want to separate from solution to the body of this resin. And then after that, so you separate your metal ions of interest by absorbing or by on the resin. And after that, you can strip off these ions that are previously absorbed and get them back in solution. But in this case, the solution will be purified. Now, of course, these exchangeable ions here can be modified using materials engineering. You can have whatever functional group you want, depends on the metal that you want to separate to improve selectivity. It is a good processing technique in the case of a very low concentration of ions in solution. So it is mainly used for water purification. It is used in actually in rare earth solution purification, but after the development of solvent extraction process, then the solvent extraction becomes more common in than this type of technique. And these are some of resins, names and structures that are applied for extraction and separation of rare earth. Some of them are used for heavy rare earth, and some of them are used for lighter rare earth. Some of them are used in nitric acid solution and other in hydrochloric acid solution. Crystallization also is one of the techniques that are used to separate rare earth compounds, and crystallization in general. In a crystallization process is you convert the material or compound in solution into a solid state by change in temperature. And usually some material or reagents are added to aid the crystallization, which include, some of them are shown here, for example, ammonium nitrate double salts. Usually they are used for the removal of lanthanum and praseodymium and neodymium. Magnesium nitrate double salts are also used usually for the medium rare earth elements, and for the heavier rare earth element or yttric group, these bromates and ethyl sulfates, they are also used. Precipitation technique using either hydroxide or oxalic acids or double salts are also utilized to precipitate rare earth compounds. Solvent extraction, again, is now it is one of the most famous techniques that are used in hydrometallurgy in to purify solutions or leachate solution. The thing is, this can be done at very large scale, and plus the whatever solvent that you are using depends on the again, the flow sheet depends on the nature of your material, but there is always provision for recycling material and solvent to your process. The solvent extraction simply is when you mix organic phase with aqueous phase. But in the case of, so it is a kind of liquid-liquid separation. But in the case of solvent extraction application in separation of metals, actually the organic phase is usually mixed with an extractant molecules. So the key of any solvent extraction is the selectivity of the extractant molecules part of the organic phase. And there are many extractant molecules that have been developed and applied at commercial scale, and some of them they are some other reagents are novel, but they are not applied at larger scales, and I'll discuss some of these. But usually when you mix your aqueous phase that has, let's say your rare earth elements into an organic phase that has extractant that are selective for rare earth, and then you mix, and then you do the phase separation. So in this case, your rare earth will complex with the extractant molecule and move to the organic phase, and then you can separate the phases. So now your rare earth is in the organic phase, and then you take the organic phase and mix it with what we call stripping solution, which is an aqueous solution of a specific acidity, and then you strip the rare earth compound back to aqueous phase, but in this case, you have a pure or almost a pure solution of rare earth compounds. Now, of course, the purity depends on how many stages and how complex is your material, how complex is your feed material. And usually the solvent extraction process is assessment of the efficiency can be done using any of these, all of these calculation, extraction efficiency, stripping efficiency, separation factor, and distribution coefficient. CA here refers to the.
Hi, Lana.
I'm going.
If you don't mind me interrupting, we made a mistake and gave you the most complex topic, and we are running out of time.
Okay, I will. Okay, I will. Can you give me another 2 minutes?
Yeah, another 2 minutes, and then maybe we would have time for one short question. Thank you very much.
Okay. So this is the solvent extraction. The conventional extractant are shown in this slides. DIPA here is one of the most common used extractants and selective extractant for the separation of rare earth. TOPO and TPB also are used. In new types of extractants involve ionic liquid. They are very famous. They are molten salts. They have anionic part and cationic part. And now, with the development in the materials engineering and all of these software like molecular dynamic simulation, it allows for the design of more selective ionic liquids or functionalized ionic liquid to enhance the selectivity and enhance the separation kinetics. The problem of ionic liquid is the production, large scale production of this material. But these are promising reagents that they are highly selective that can be used as extractant in the solvent extraction process. So these are the last two slides. This is the hydrometallurgical processing of bismuthite concentrate that contains 60% of rare earth oxides using solvent extraction and then selective reduction. It starts with a calcination, then leaching in concentrated HCl to remove cerium. And then the supernatant here goes to many stages of solvent extraction. The first is to separate heavier and lighter rare earth, and then ion precipitation to remove iron using soda ash, and then apply of DIPA again. So again, this is DIPA is utilized here for as an extractant in kerosene. And then again, you can see similar separation processes, and you end up with europium, which is in the oxidation state 3 here in a chloride solution, and then you add zinc to reduce it to europium 2. And after that, you add sulfuric acid. Sulfuric acid to convert europium 2 to europium sulfate, and then calcination can again convert the sulfate to oxide. So this is actually some current and potential sources of rare earth. So you have here Mountain Pass, and which produces rare earth oxides. Currently, they are shipped off country, but soon they will have their own refining facility. Mineral sands in Georgia that produce 3,000 tons per annum of rare earth concentrate as well. But previously the concentrate is shipped to China, but now it is shipped to Energy Fuel in Utah. Other sources of unconventional sources of rare earth involve byproducts of phosphate mining, especially the phosphogypsum, which has up to 600 ppm of rare earth. Other unconventional sources also include the coal ash from coal mining. So rare earth and other critical metals are concentrated in finer fraction, which is usually mostly the silicate mineral that are in the coal ash. There is a pilot demo for rare earth concentrate recovery now, but as far as I know, there is no larger scale operation of this.